We're going to be talking about predicting products. We're going to be talking about predicting products. So last class we talked about the types of chemical reactions. What were the 5 types of chemical reactions? Sorry? No one watched the video yesterday, that's okay. So we have synthesis, decomposition, single replacement, double replacement, and combustion reaction are the 5 major types. Now, you have to be able to identify those types of reactions, but in addition to that, you have to be able to tell what type of reaction you have just looking at the reactants. So what was the general form of a synthesis reaction? What was the general form of a synthesis reaction? You guys really didn't do your homework yesterday. Okay, well it was A plus B produces C. Now, if I ever ask you in this course to predict the products of a synthesis reaction, it's going to be really obvious. I'm not going to be giving you a complex problem where you have 2 compounds that form one large compound, because you guys don't have the ability to discern that is a synthesis reaction. What I will give you is 2 elements. So for any synthesis reaction I give you, A and B here are going to represent 2 different elements. So for predicting synthesis, reactions, the reactants will be 2 elements. The reactants will be 2 elements. So, super simple example would be something like aluminum plus, say, sulfur. Aluminum, say, plus sulfur. By the way, elemental sulfur is S8. What kind of compound would this form? Anyone want to take a stab at it? What is the ionic compound that is formed between aluminum and sulfur? When you're forming an ionic compound, what are the steps? You have to get proficient at this, right? We're coming close to the unit test. What are the steps that you need to do? Yeah, what are the charges of aluminum and sulfur? Aluminum's 3+, what about sulfur? 2 negative, excellent. And then you say, okay, well in total how many electrons were donated, received, right? What was the total charges? And then how many of each you need? Which will give you Al2S3. Al2S3. So, if you don't know how I got that, you need to forget about balancing, you need to forget about everything we're doing right now. You have to go back and you have to practice ionic bonding. Without this skill, you can't do balancing because you can't come up with the skeleton equation. Alright, so how do I balance this one? This one's super awkward to balance, actually. Whenever you have, now I'm not going to be mean on your test. I'm not going to give you one like this, but you have 8 sulfurs here and 3 here. The only way to truly get equal numbers on each side is to use actually the LCM. We got to find the lowest common multiple between 3 and 8. Because again, the aluminums, it doesn't really matter in the end, because what can we do over here? Yeah, we can put whatever number we want there, right? So that doesn't matter. What is the LCM between 3 and 8? What is the LCM between 3 and 8? 24. So this will be 3, 8, and we have 16 aluminums. Stupidly awkward to balance. But potentially could ask you a question like this. So whenever you're given a synthesis reaction, whenever I ask you to predict the products, you're always going to have 2 elements, and they're going to be forming an ionic bond. So that's how you can identify you have a synthesis reaction. You have 2 individual elements. On the flip side, how do you think you can identify a decomposition reaction? So that's how you're able to identify a synthesis reaction, right? You'll see 2 individual elements. What about decomposition? 3, not 3. So decomposition is the opposite of your synthesis. This is where you have one thing becoming many things, right? Synthesis, you have many things becoming one thing. Decomposition is the complete opposite. So decomposition reactions are pretty easy to identify. The reason is, to identify there will be only one reactant. That's how you can tell it is a decomposition reaction. Right? So if I give you one reactant, you should know right away you have a decomposition reaction. And I'm going to be kind to you guys. I'm pretty much only going to give you things that are very obvious in how they break down. I'm not going to be giving you extremely large complex molecules and expect you to break those down. You're going to be given pretty simple, usually ionic compounds. I may give you a decomposition of something we explore in one of our labs though. So it is important when we do that types of reactions lab that you understand all of those reactions we do in that lab very well. Because there is a couple that aren't ionic bonds breaking down. We're going to do them in that lab, and you do need to know those reactions. But for all intents and purposes, most of them are going to look like this, where you have, say, I don't know, let's say this. Right? You have one reactant. It's pretty obvious that this is a decomposition reaction. What is this going to break up into? Can only really break up into 2 things here. Iron and chlorine. Why did I put a 2 there on chlorine? Excellent. It's one of the Hofbrinkel elements, right? So chlorine is one of your Hofbrinkel elements. Remember, you cannot forget about Hofbrinkel. So many students forget about him and lose a ton of marks as a result. So how am I going to balance this one out? Here you can follow my tip. If it's odd, make it even. It always makes things easier to balance. Yeah, we can put a 2 here to make it nice and even. Now we have 6 chlorines. So how am I going to balance chlorines on this side? 3. And then iron? 2, yeah. So that's an example of a decomposition reaction, right? If I ever ask you to predict products of decomposition, you're going to be given a single reactant. That's how you know it's decomposition. So again, synthesis, you're going to be given 2 elements. Decomposition, you'll be given 1 reactant, 1 compound. Now, for single replacement, this is where things get a little confusing. Because up to this point, it should be pretty straightforward for those two. I can really only present them to you in one way. But with single replacement, or displacement, either terminology is correct, it takes the general form like this, where you have one partner switching out for another. Now remember, will 2 negatives make a bond? 2 negative charges, will they make an ionic bond together? No. Will 2 positives make a bond together? No, right? What does make a bond? Yeah, opposite charges, right? Opposite charges attract, like charges repel. So keep that logic in mind. Because what you're going to be given here is an ionic compound, and you have to make sure that you switch the like charges. So to identify you will be given an ionic compound reacting with an element. And when I say element here, I don't mean just a single atom. I'm also referencing the diatomic molecules as well. That's what I mean when I say element. Now, remember grade 9 electrostatics, only opposite charges will form a bond. Therefore, you must only switch like ions, right? You should only switch ions of the same charge. Now this may look a little confusing, but once you see it in an example, it'll make perfect sense. So let's say I gave you magnesium oxide reacting with, let's say, fluorine gas. Magnesium oxide reacting with fluorine gas. Now, what charge does magnesium have when it forms an ionic bond? Positive. We don't have to worry about the magnitude at this very second, but you're right, it is 2. So it forms a positive. What about oxygen? Does it form an anion or a cation? Anion, right? It's negative charge. And the nice thing about ionic compounds is, what do we always list first, the cation or the anion? Okay, right, the cation, right? We list the cation first, and then we list the anion second. So when you're talking about your ionic compound, you don't really need to worry too much about what has what charge, because it's given to you in the order of the elements that are provided, right? Cation is always listed first, anion is listed second. This is where you need to do the thinking though. When fluorine becomes an ion, fluoride ion, what charge will it carry? It's a halogen, has 7 valence electrons. What does it want to do? Gain one more, so what charge will it have? Negative, right? So fluorine has a negative charge. Now, obviously, when we're talking about single replacement reactions here, we are going to be switching our like ions because two negatives won't form a bond, right? Two negatives will repel each other. So when this reaction happens, these like ions are going to be switched, so that we still have a positive bonding with a negative. So we get MgF2 and O2. Right, we still have a positive bonded to a negative here, and we have switched our like ions. Really important. A lot of students here, they just guess as to what they need to do. They'll go, OF2 plus Mg, right, which is not correct. Okay, so let's look at one more example, because there is another type of single replacement. You can't always just switch that element. You can't fall into that trap. You need to think about what charge this element here carries. So if I gave you, for example, let's say, oh, by the way, to balance this one, you'd have to put it through here. Al2O3 plus, I don't know, say iron. Actually, let's not do iron. Let's do zinc. What charge does zinc have when it makes an ionic bond? By the way, if I do give you a multivalent metal, I'm going to tell you the Roman numeral. I don't expect you to be able to somehow predict that. But this one I don't need to give you the Roman numeral for. What is the charge on zinc? It's going to be positive, 2 plus, right? So we have positive. What charge does our aluminum have? Positive. And what about oxygen? Negative, right? So here, again, we need to switch like ions. We need our compound to be positive bonded to negative. So what am I going to switch? Am I going to switch zinc with oxygen or zinc with aluminum? Excellent, zinc with aluminum. Right? Because we need to switch our like ions, and that gives us zinc oxide plus aluminum. Okay, so again, with single replacement reactions, when you're predicting the products, switch like ions. And you always got to ask yourself, what charge does this element have here? But again, it'll always take the same form. You're going to have an ionic compound plus some element. All right, let's now look at double replacement. In my mind, these are actually a little bit easier than single replacement. They're typically harder to balance, however, but they tend to be quite a bit easier to figure out your products. So this is the general form they take. So when you're looking at a double displacement reaction, to identify the reactants will consist of two ionic compounds. Right? Your reactants will always consist of two ionic compounds. And just like single replacement reactions, again, you must always switch like ions. So just like single replacement, you gotta switch your positives or your negatives. It actually doesn't matter which one you do because you're gonna get the same products either way. Now you're doing a bit of a do-si-do here. You're switching partners around. Now the thing that makes this, in my mind, a little easier than single replacement is in an ionic compound, what comes first, the cation or the anion? When we list them, what comes first? The cation, right? So you don't even need to really think about the charges at all because it is implicit within the way you've written your formula down, right? So cation, anion, cation, anion. And if you look at the way I've switched them, I intentionally switched them in this way. Because now look, A is a cation, D is an anion. We have cation with anion. B is an anion, C is a cation. We have cation with anion. So you can see that I have not changed the structure of my ionic compounds. It's always going to be cation followed by anion. So these ones are really, in my mind, easier to do than single replacement, but they are harder typically to make formulas for and to balance in the end. And I'll show you a good example of that. See, I can get a little mean here. I can toss in some polyatomics, some multivalent metals. We could do something like V3PO4 plus, let's say, NH4 to SO4. That looks like a complete mess, right? Looks like a complete mess. Now again, if you look, your reactants here are two ionic compounds. So this is a double replacement, double displacement reaction. So what charge does vanadium have? I don't care about the magnitude right now, just is it positive or negative? It's positive. And positive. What about phosphate? Come on, you guys know it, what is it? Right, the cation comes first, the anion is next, so yeah, so phosphate's negative. What about ammonium? Positive. And sulfate? Negative, right? You don't actually need to think about what charges they have, because again, we list cation, anion, cation, anion. You do need to think about their charges, however, when you make your ionic compounds. A lot of students here, they're very tempted to do something like this. They'll be like, okay, well I've got 3 vanadiums, 1 sulfate, and we're switching, okay, so we're going to do this. And then we're going to do this. Okay, we got that, so it's going to look like this. NH4, 2PO4, 4. And then they'll be like, okay, it's done. Why is this like super wrong? It's balanced. I have the right number of phosphates and ammoniums, but why is this super wrong? Think about it. Why is that so wrong? Ionic bonds, what always has to balance? What always has to balance? Your charges. Here they don't balance at all, right? At all. This is a good example here because you guys can see the charges on your periodic tables. What charge does ammonium have? What charge does ammonium have? Look it up. Yeah, you're right. What is it? 1. Positive 1. What charge does phosphate have? Yeah, you're right. 3 negative. So clearly, you're not going to need 4 phosphates and 2 ammoniums. It makes no sense. So each of your products, if you haven't figured it out yet, each of your products you need to treat as an individual problem when it comes to ionic bonding, right? You have to isolate it and be like, okay, well, these are my charges. This is the total number of electrons donated, received, and as a result, how many of each ion do I need? You always have to keep that that rhetoric going in your mind, right? You always have to keep that process going. And that's something that only comes with practice, and I have a feeling a lot of you are not doing enough of that. So you need to practice more. So, vanadium, what charge does vanadium have there? What's the magnitude of the charge? You're right, it is positive. Oh, you're good, yeah. It's 4 plus. If you don't know where that came from, you need to work on multivalent metals. So it's vanadium 4 plus, and it's going to be bonded with which ion here? Because we're going to switch. It doesn't matter. You can switch your positives or switch your negatives. We'll switch our negatives here. Okay, we're switching like ions, so it's going to be bonded with sulfate. So it's going to be VSO4 2 plus, and then we have ammonium bonded with phosphate, and ammonium's +1 phosphate is 3 minus. This gives us NH4 3 PO4. So again, figuring out the partners for a double displacement reaction is pretty simple, but again, it's going to really test your knowledge of ionic bonding. And balancing for that matter. How would I balance this one out? Let's start with vanadiums. How would I balance out vanadium? Where am I going to put the 3? Yes, in front of this vanadium here, yep. Let's balance out sulfates. Where am I going to put a coefficient to balance out my sulfates here? Well, we have 6 here. How do I get 6 on this side? What am I going to put right here? A 6. And let's balance out our ammoniums. I've got 12 ammoniums here. How am I going to get 12 here? I'm not going to put 12 there. There we go. 4 times 3 is 12. Are my phosphates balanced? Are they balanced? Yes. Okay, there we go. So you can see that most students here, they don't struggle with the whole switching part here. They're going to struggle with coming up with the correct formulas. So practice, please. All right, last type of reaction. Combustion reaction. Now the hydrocarbon combustion reaction, these are probably the easiest of all for predicting products. Because what will your reactants always be? What will your reactants always be for hydrocarbon combustion? They don't change. The general form is a hydrocarbon plus oxygen. And what are your products? Always. You breathe one of them out. CO2. The other ones, you need to drink it every single day, otherwise you die. H2O. Maybe not every day, but most of us. Okay, so hydrocarbon plus oxygen gives you CO2 and H2O. So these are perhaps the easiest to identify because your reactants are always going to be the same. So, to identify, reactants will always be a hydrocarbon reacting with oxygen. And what are my products always going to be? CO2 and H2O. So, these are probably the simplest. You just need to remember those two things. So for example, let's say I gave you C6H14 plus O2. Is C6H14 a hydrocarbon? Yes, it's composed of carbon and hydrogen, right? It's in the name. Carbon, hydrogen. I know it's a little confusing because most of the time hydro we mean water, but here it means hydrogen and carbon. So we have a hydrocarbon and oxygen, and what are my products going to be? Always, right? Easy. So if you see that, you automatically know what your products are. This one's a little trickier to balance, however. What are we going to balance last? Oxygen. Let's balance our carbons. What am I going to do? What am I going to put right here? Good job. What about right here for my hydrogens? 7. How many oxygens do I have on this side? No, I do not have 7. How many oxygens do I have on the product side? We have 12 plus 7, which is 19. There we go. 19. So 19. I have to get 19 oxygens on this side. How am I going to do that? How am I going to do that? How am I going to get 19 oxygens? Well, what's 19 divided by 2? What's 19 divided by 2? Well, I'll give you a hint. 18 divided by 2 is 9. 20 divided by 2 is 10. 9.5. There you go. Now, can you have half of a molecule? No. So what do I need to do? I have to double all my coefficients, right? Doubling all of my coefficients gives me 2, 19, 12, and 14.